In this article, we study about if the differential equation is not exact, so how can we solve the given first order, first degree differential equation. So, first here we describe method 1 in the differential equation. In the differential equation, m dx plus n dy is equal to 0 if m is equal to y multiplied by f1 xy and n is equal to x f2 xy, then integrating factor this is equal to then integrating factor is 1 upon mx minus ny. Here m dx plus n dy is equal to 0. This is the first order first degree differential equation. If in this differential equation del m by del y is not equal to del n by del x, then this differential equation is not exact. If the differential equation is not exact, so we use here method 1 if m is equal to y multiplied by f1 xy and n is equal to x multiplied by f2 xy, then here we multiply the above equation m dx plus n dy is equal to 0 by the integrating factor 1 upon mx minus ny. If the given differential equation m dx plus n dy is equal to 0 is not exact and m is equal to y f1 xy and n is equal to x multiplied by f2 xy, then we multiply this differential equation by the integrating factor 1 upon mx minus ny, and after multiplication this equation will be exact. So here we take some example on this article. So that is x square y square plus xy plus 1 multiplied by y dx plus x square y square minus xy plus 1 multiplied by f dy. Here we can see first we compare this given differential equation by m dx plus n dy is equal to 0. Here we can see m is the coefficient of dx. So here the coefficient of dx is x square y square plus xy plus 1 multiplied by y, and n is the coefficient of dy, that is x square y square minus xy plus 1 multiplied by x. Now here m multiply this y and open the bracket and y multiply in all these terms, so we get x square y cube plus xy square plus y. Similarly here we multiply this x in all these terms, so we get here x cube y square minus x square y plus x. Now we differentiate this m partially with respect to y. So here we can see here this x square y cube, here we differentiate this partially with respect to y, so x square is constant here, and when we differentiate y cube with respect to y we get 3y square, and when we differentiate xy square, so x is constant here and differentiation of y square with respect to y, that is 2y, and differentiation of y with respect to y, that is 1. Now we differentiate here and we get del n by del x. So when we differentiate this x cube y square with respect to x, so this y square is constant, and differentiation of x cube with respect to x, this is 3x square, minus here we differentiate x square y with respect to x, so y is constant here, and differentiation of x square with respect to x, that is 2x, and differentiation of x with respect to x, that is 1. Here we can see this del m by del y is not equal to del m by del x. So del m by del y is not equal to del n by del x. So the above given equation is not exact. So we use here integrating factor. We can see here m is of the form y multiplied by f1xy and n is of the form x multiplied by f2xy. Here m and n both are in the form y f1xy and x f2xy. So here, here integrating factor I dot f means integrating factor is 1 upon mx minus ny. So first we calculate here mx minus ny. So we multiply x in m, so we get here x multiplied by x square by q. So this is s²y². X multiplied by xy square, so we get here x square y square, and x multiplied by y we get here xy. Similarly here n multiplied by y and here negative sign, so all the sign will be changed. So this is minus s³y³. Here we multiply y by x square y, so this is plus s³, this is x square y square, and this will be negative sign, and x multiplied by y we get here xy. So we can see here this s³y³ is cancelled by s³y³, and this plus xy cancelled by this is minus xy. So here x square y square add by x square y square, so we get here 2x square y square. So this is mx minus ny. So the integrating factor is 1 upon mx minus ny is equal to 1 upon 2x square y square. Since this is the first order given differential equation is in the form m dx plus n dy is equal to 0. So first we compare this given differential equation by m dx plus n dy is equal to 0. Here the coefficient of dx is m, here the coefficient of dx is x square y square plus xy plus 1 multiplied by y. Similarly here the coefficient of dy is n, so the n is x square y square minus xy plus 1 multiplied by x. So first we differentiate m partially with respect to y, we get del m by del y. Similarly we differentiate partially with respect to x of n, so we get del n by del x. Here we can see that del m by del y not equal to del n by del x. So the above given equation is not exact. Here we can see m is of the form y multiplied by f1xy and n is of the form x multiplied by f2xy. So here integrating factor is 1 upon mx minus ny. So we calculate here first mx minus ny. For calculating this, multiply m by x and n by y, and then find the difference. So mx minus ny, this is equal to 2x square y square. So integrating factor is 1 upon mx minus ny, that is 1 upon 2x square y square. If we multiply the above given differential equation by the integrating factor, it will be reduces into the exact form. So we multiply the given equation by 1 upon 2x square y square. So it is equal to here x square y square plus xy plus 1, and all the terms divide by 2x square y square, 2x square y square, and here 1 upon 2x square y square. So sorry, this is x square y cube, this is xy square, and here this is y. And in the second bracket we multiply this 1 upon 2 x square y square in m, so we get here s cube y square by 1 upon 2 x square y square minus x square y divided by 2 x square y square plus x divided by 2 x square y square dy is equal to 0. In the above given differential equation, we multiply whole equation by 1 upon 2 x square y square, that is the integrating factor. Solving this, so we get here y, this x square cancelled by this, and here y upon 2 plus here this y square cancelled by this y square, we get 1 upon 2x, and in this term we cancel out this square by y, so we get 1 upon 2x square y dx. In the second term, here y square cancelled by this y square, this x square cancelled by this power cube, so this is x by 2. Here this x square cancelled by this square, y cancelled by this square, so here we get 1 upon 2y, and here 1 upon 2xy square dy is equal to 0. Now this equation is reduced in exact form. If we find del m by del y and del n by del x, so we can see here both are equal. So we write the solution of this differential equation, that is m dx plus n1 dy is equal to c. Here m is this, m is y upon 2 plus 1 upon 2x plus 1 upon 2x square y, and n1 we obtain n1 from m, and n1 is independent from x. So this, in this term here is x, and in this term is also x, so we take only the term minus 1 upon 2y. We know that here n1 is obtained from this m, and we take those terms in which x is not present. Here this is x and here is x, so we leave these two terms and taking only one term, that is minus 1 upon 2y. So in this integration y upon 2, this is constant, and integration of dx, this is x. Here 1 upon 2 is constant, and integration of 1 upon x with respect to x, this is log x, and here 1 upon 2y, this is constant, and when we integrate 1 upon x square, so x square goes to the numerator and the power will be negative, that is x to the power minus 2, and when we integrate x to the power minus 2 with respect to x, so we get x to the power minus 1 upon minus 1, that is minus 1 upon x. And here this is 1 upon 2, this is constant, so it outside the integral sign, and integration of 1 upon y, this is log y. Here we taking, this is constant, c is c1, so we write here this is c1, suppose, so this is c1. Now we multiply whole the equation by 2, so we get here xy plus log x minus 1 upon xy minus log y is equal to 2c1, and c1 is constant, 2 is constant, so product of 2 and c1 is also constant, that is c. So we write here xy minus 1 upon xy plus log x minus log y is equal to c. So this is the solution of the given first order first degree differential equation. If the given differential equation m dx plus n dy is equal to 0 is not exact, then we use here the method 1. First we see if m is equal to y multiplied by f1 xy and n is equal to x multiplied by f2 xy, then the given differential equation multiplied by the integrating factor and reduces to exact form. Here the integrating factor is 1 upon mx minus ny. Thank you.